Hello there, and welcome to Sleeping Science Channel. There's a place on our Earth that has never been touched by the light of the sun. A place of unfathomable depth, of perfect stillness, so profoundly withdrawn from the world we know that it might as well exist on another planet. It rests beneath the immensity of the Pacific Ocean, under thousands of meters of icy, pressing water, in a darkness so absolute it seems to have no beginning and no end. Most of us will never set foot there, never come close. And yet, it is real there, silently lurking at the bottom of our world, harboring wonders we are only just beginning to decipher. Welcome to Frequent Science. Tonight, we embark together on a journey to a place where very few humans have ventured. We will descend slowly, gently, one silent truth after another, into the deepest abysses of the earth. There is nothing you have to do tonight but breathe and listen. The world above can wait. Tonight, it belongs to the depths. So settle in. Let your shoulders drop. Let the weight of the day drift away, and let the ocean carry you. The Mariana Trench is the deepest known point on the Earth's surface. Somewhere in the western Pacific Ocean, not far from a string of small islands called the Marianas, the ocean floor collapses. It plunges, and continues to plunge, carving a long crescent-shaped gash in the ocean floor, stretching for nearly 2,400 kilometers. At its most abyssal point, a place named Challenger Deep, the bottom lies almost 11 kilometers below the sea surface. To grasp what 11 kilometers of depth represents, imagine this. If you took Mount Everest, the highest mountain on Earth, and dropped it into the Mariana Trench, its summit would still be more than 2 kilometers underwater. The entire mountain would disappear, and there would still be open water above it. The trench doesn't just swallow mountains, it completely conceals them and still has vast free spaces. And yet, despite its immensity, the Mariana Trench is a place of calm. There are no crashing waves there, no wind, no storms, just the pressure, the darkness, and the slow passage of time. It has been there for millions of years, waiting patiently beneath the sea. Long before humans walked the earth, the trench was already ancient. It will be there long after we are gone. And strangely, in the heart of the night, this thought is not frightening at all. It is simply serene. The trench was first discovered in the 1800s during a memorable voyage called the Challenger Expedition. In the year 1872, a British ship, the HMS Challenger, embarked on one of the most ambitious scientific odysseys in human history. The mission, simple in concept, was extraordinary in its execution. The crew would sail across the world's oceans to attempt to unlock their mysteries. They would measure depths, take samples, observe temperatures, and record every one of their discoveries. For 3.5 years, the Challenger crisscrossed the seas, and one memorable afternoon in the western Pacific, the crew lowered a weighted line into the water and watched it sink, and continue to sink far beyond anything they had measured before. The line finally went slack at a depth that stunned the scientists on board. They had found a place in the ocean deeper than anything known until then. They couldn't imagine what the trench actually looked like, had no submarines, no cameras, no instruments capable of peering into that darkness. All they had was a line, a weight, and the silent shock of watching it descend into an abyss that seemed endless. They named their discovery after the ship itself, Challenger Deep. And that name has stuck ever since, a small human imprint left on one of the most inhuman places on Earth. Imagine what it must have been like to be on that ship, the sun at its zenith, the gentle Pacific breeze, the ordinary sounds of a working ship. And then, far below, in a darkness none of them could see, the rope stretching into the longest silence imaginable. The water pressure at the bottom of the trench is more than 1,000 times greater than surface pressure. At sea level, the air around us exerts a certain force on every surface. We are so accustomed to this pressure that we don't feel it at all. It's simply the way the world is. But as you descend into the ocean, something changes. For every 10 meters of descent, the pressure increases by approximately 1 additional atmosphere. The deeper you go, the more the weight of all the water above presses down on everything below. At the bottom of the Mariana Trench, the pressure is approximately 1,100 times greater than at the surface. This means that every square centimeter of surface bears a force that would crush almost anything we could build or take down. Steel bends under such pressure. Glass shatters. The unprotected human body would not survive even a fraction of the descent. And yet, life is present there. Creatures that have never known another world move silently through this crushing darkness, as if the pressure were simply the air they breathe. Because for them, it is. Their bodies have evolved over millions of years to adapt so perfectly to their environment that pressure is no constraint for them. They are shaped by it, balanced within it, in harmony with a force that would instantly destroy us. There is something deeply soothing about this idea, that even in the most extreme place on Earth, life has found a way to belong there, to be perfectly at home, in a world that seems designed for nothing at all. The Challenger Deep is located at the southern end of the trench and is the deepest point on Earth. The Mariana Trench is long and winding, like a great scar drawn on the Pacific floor by an ancient, patient hand. But within this trench, there are deeper and shallower sections, an uneven topography sculpted by forces acting on geological timescales. And at the southernmost end of the trench, there is a place that plunges deeper than all others. This is the Challenger Deep. For years, scientists debated the exact depth of the Challenger Deep. Each new expedition, with more precise instruments, brought back a slightly different figure. Early measurements put it at approximately 10,900 meters. Later surveys pushed that figure slightly higher. More recent efforts, using sophisticated sonar mapping systems, have recorded depths approaching 10,925 meters, or even more, depending on the methods used. The uncertainty itself is remarkable. We don't know the deepest point on Earth within a few meters. The ocean floor is so remote, so difficult to reach and measure accurately, that the trench easily keeps its secrets. We have mapped the surface of Mars in more detail than the bottom of our own ocean. The universe beyond our world is, in some ways, better understood than the world beneath our feet. But the Challenger Deep does not care about its mystery. It has shown very long patience. Only a very small number of people have had the opportunity to descend to the bottom of the Mariana Trench. More individuals have walked on the surface of the moon than have plunged to the deepest point of the ocean. This figure is striking. The moon is approximately 384,000 kilometers away. The Challenger Deep is less than 11 kilometers beneath the Pacific surface, and yet the journey to the moon has proven more feasible, or at least more frequently attempted, than reaching the deepest part of our own planet. The first humans to descend into the Challenger Deep were Jacques Piccard and Don Walsh, who made the journey in January 1960 aboard a vessel called the Trieste. The Trieste was a bathyscaphe, a steel sphere attached beneath a large gasoline-filled float, which provided buoyancy. It was neither elegant nor fast. The descent took nearly 5 hours, but when Piccard and Walsh reached the bottom, they found something completely unexpected. Creatures lived there. Fish, or animals that resembled fish, moving calmly across the sediment at the bottom of the world. Life had found its way into the most extreme corner of the ocean. It was, in all respects, one of the most astonishing moments in the history of exploration. After Piccard and Walsh, the abyss was largely neglected for decades. The difficulty and cost of reaching such a depth made regular expeditions almost impossible. It was not until many years later that other explorers began to follow in their footsteps. Each descent revealed something new. Each journey into the depths brought back more questions than answers. The bottom of the trench is covered by a soft layer of sediment that has accumulated over millions of years. When you imagine the deepest place on Earth, you might visualize bare rock, jagged volcanic formations, or a scene of raw geological violence. But the actual bottom of the Mariana Trench is much softer than that. The floor of the Challenger Deep is carpeted with a pale, silty sediment, a layer of material that has drifted down from the upper waters for millions and millions of years. This sediment is composed of tiny particles, the remains of microscopic organisms that lived and died in the sunlit waters far above, mineral grains carried by ocean currents from distant parts of the seabed, dust carried by winds from continents, and even particles from space, tiny fragments of cosmic matter that have settled gently through the atmosphere, through the ocean, and come to rest in the deepest part of the world. The sediment accumulates extremely slowly. In the deep ocean, the accumulation rate can be as low as a few millimeters per 1,000 years, which means that the upper layers of sediment at the bottom of the trench can represent not thousands, but millions of years of calm, constant deposition. Every centimeter of this pale, soft layer is a record of time written in the smallest of scripts. To disturb it is to disturb history. Submersibles that land on the bottom kick up small clouds of sediment that disperse, hang for a moment in the water, and then slowly settle again. The trench accepts the disturbance calmly, as it accepts all things with a patience measured in geological eras. Despite the darkness and pressure, the Mariana Trench is home to a surprising variety of life. The idea that nothing could live at the bottom of the Mariana Trench seems perfectly reasonable. No light, immense pressure, near freezing temperatures, a crushing, silent darkness that has never been touched by sunlight in the entire history of Earth. These conditions hardly seem hospitable. And yet, the abyss is not empty. It teems with life. Not the colorful, charismatic life of coral reefs, perhaps, but life nonetheless. Strange, adapted, quietly extraordinary creatures that have made the deepest place on Earth their home and seem perfectly at ease there. Scientists have discovered over 200 species of organisms in the Mariana Trench alone. Bacteria live in the sediment, processing chemicals in ways that would be impossible closer to the surface. Tiny crustaceans called amphipods swarm in remarkable numbers, sometimes covering the bottom in pale, scurrying crowds. Fish have been filmed swimming calmly in the darkness, their pale bodies and large eyes giving them an almost ghostly quality. Foraminifera, single-celled organisms encased in delicate shells, drift through the water and settle on the bottom. Life in the deep doesn't announce itself. It doesn't shimmer, flash, or shout. It simply exists, quietly and persistently, in the most extreme environment our planet has to offer. And there is something beautiful in that silence, something that, in the dark hours of the night, feels very much like rest. Amphipods are among the most abundant creatures in the trench and can grow to surprisingly large sizes. In most oceans, amphipods are tiny. They are crustaceans related to shrimp and crabs, and they spend their lives scavenging in sediments, consuming any organic matter that drifts down from above. In shallow and midwaters, they rarely exceed a few centimeters. But in the deep ocean, something different happens. In the dark and cold of the Hadal Zone, the deepest parts of the ocean, named after Hades, the mythological underworld, amphipods can reach sizes that would seem impossible to anyone who has only seen their shallow water cousins. Some species found in the Mariana Trench have been measured at 28 centimeters or more, the size of a small lobster. This phenomenon of deep-sea gigantism is not fully understood. It may be related to the cold temperatures, which slow metabolism and allow organisms to live longer and grow larger over time. It may be related to the scarcity of food, which, paradoxically, seems to favor larger body sizes in some species. Or it may be related to pressure in a way that science has not yet fully unraveled. Whatever the cause, the result is striking. Mariana Trench amphipods move through the darkness in large drifting swarms, pale and translucent, gathering around anything that sinks to the bottom. A piece of food dropped into the trench will be surrounded by thousands of them within hours. They are patient creatures, perfectly adapted to their world, waiting quietly in the darkness. The water temperature at the bottom of the trench remains near freezing year-round. Near the surface, the ocean changes and shifts with the seasons. In summer, the upper layers warm up. In winter, they cool down. Storms churn the water and mix temperatures. There is variability, a rhythm, a kind of breathing that the surface ocean performs throughout the year. But at the bottom of the Mariana Trench, none of that reaches. The water there is cold and stable, hovering a few degrees above freezing. No matter what happens on the surface, seasons have no meaning in the depths. The temperature changes almost imperceptibly from year to year, or from decade to decade. Time, in a thermal sense, has essentially stopped. The cold is not hostile, at least not for the creatures that have adapted to it. For deep-sea organisms, cold is simply the way things are. Their enzymes function at low temperatures. Their membranes are flexible in the cold rather than rigid. Their chemistry has been shaped over millions of years to operate precisely at the abyss's temperature. There is something deeply soothing about this kind of constancy. A place where the temperature is always the same, where nothing moves or stirs, where the cold is stable, deep, and reliable. Like the silence of a very still night, where even the wind has fallen asleep. Hydrothermal vents near the trenches produce superheated, mineral-rich water and support entire ecosystems. The deep ocean is not uniformly cold. In some places, where the Earth's internal heat finds pathways through the ocean floor, water is heated to extraordinary temperatures and forced to rise through cracks and chimneys in the rock. These are hydrothermal vents, and they are among the most remarkable environments on Earth. The water emerging from a hydrothermal vent can reach 300 degrees Celsius or more. It does not boil only because the pressure there is so extreme that even water at that temperature remains liquid. The superheated water is rich in dissolved minerals from the rocks it has passed through on its ascent. When this mineral-laden water meets the near-freezing water of the deep ocean, the minerals precipitate and form towering chimneys of dark rock, some of which reach several meters in height. Because they release dark, mineral-rich water, they are called black smokers. Around these vents, life thrives in a way that stunned scientists when they were first discovered in the 1970s. Tube worms several meters long sway gently in the currents. White crabs and shrimp congregate in extraordinary numbers. Mats of bacteria cover all available surfaces. All of this is powered not by sunlight, but by the chemical energy of minerals from the earth. It was the discovery of hydrothermal vent ecosystems that prompted scientists to seriously consider the possibility of life existing on other worlds. If life can thrive in total darkness, under crushing pressures, surviving on chemical energy without any sunlight, then the rules for life's existence had to be entirely rewritten. The Mariana Trench formed through the movement of tectonic plates, a process that has lasted for tens of millions of years. The earth beneath our feet is not still. The planet's surface is divided into enormous sections called tectonic plates, and these plates are always in motion, though so slowly that we cannot perceive it within a single lifetime. They drift across the planet's surface at roughly the rate our fingernails grow, a few centimeters per year. But over millions of years, even this slow movement produces spectacular results. When two plates meet, one usually slides beneath the other in a process called subduction. The overriding plate bends inwards towards the Earth, and as it descends, it carves a trench in the ocean floor. The Mariana Trench formed in exactly this way. The Pacific Plate is slowly sliding beneath the Mariana Plate, and where it bends towards the Earth, the ocean floor sinks to its greatest depths. This process has been ongoing for approximately 180 million years in this region of the Pacific. The trench itself, in its approximate current form, has existed for tens of millions of years. It is older than most mountain ranges on Earth. It is older than most mammals that have walked the surface, and it is still forming. The plates continue to move. The Pacific Plate continues to descend. The trench could be slightly deeper tomorrow than it is today, and slightly deeper in 1,000 years than it is now. It is not a fixed thing. It is a living geological process that unfolds with a patience that makes human history seem very brief indeed. Earthquakes occur frequently in the Mariana Trench region due to tectonic activity. When tectonic plates move against each other, they don't always do so smoothly. The enormous forces involved cause stress to build up along the boundaries between the plates. And when this stress is finally released, an earthquake results. The Mariana Trench region is one of the most seismically active places on Earth. Earthquakes are frequent there, though the vast majority are weak enough to be felt only by sensitive instruments and not by anything living on the surface. Occasionally, larger events occur, sending shockwaves through the Earth and generating tsunamis that can travel thousands of kilometers across the Pacific. But deep within the trench itself, earthquakes produce a different kind of experience. Pressure waves travel through the water and through the sediment, moving slowly through the darkness. Whatever lives there endures these tremors as it endures everything else, with patience, without drama, simply continuing to exist in the way that deep-sea creatures do, unhurried and unafraid. The Earth is restless, but the depths accept its restlessness calmly, as a very old and very patient thing accepts the small disturbances of a younger world. Sound travels differently in the deep ocean, and the trench is remarkably full of noise despite its apparent silence. We tend to think of the deep ocean as silent. All that darkness, all that distance from the world above, all that weight of water pressing down, silence seems to be the natural result. But the deep ocean is not silent at all. Sound travels through water far more efficiently than through air. In fact, sound travels through water about 4.5 times faster than through the atmosphere, and it can carry over extraordinary distances. The deep ocean has a layer called the SOFAR channel, short for sound fixing and ranging, where conditions are ideal for sound to travel particularly efficiently. Whales are known to communicate across entire ocean basins using this channel. Mariana Trench, sounds arrive from extraordinary distances and from all directions. The rumble of earthquakes, the cracking of tectonic plates, the clicks and calls of distant marine animals above, the distant hum of ship propellers passing overhead, the sounds of the surface world making their way through thousands of meters of water to the bottom of the earth. Scientists lowering hydrophones, underwater microphones, into the trench have been surprised by all they have recorded. The trench, it turns out, listens to the entire ocean. Everything that makes a sound up there eventually finds its way here, muffled and distant and transformed by the journey, but present nonetheless. In the deepest part of the ocean, the world is never completely silent. It is full of echoes. A single descent to the bottom of the Challenger Deep takes several hours. The pace of the deep ocean is not ours. We are creatures of speed and urgency, accustomed to moving quickly through the world, covering distances in a few hours that once took weeks or months. But the depths do not accommodate speed. A submersible descending to the Challenger Deep travels slowly. The calculations of the descent are simple, but the experience they provide is profound. At a descent rate of about 30 meters per minute, which is typical for a heavily weighted submersible, the journey to the bottom of the Challenger Deep takes nearly 6 hours. 6 hours of darkness, increasing pressure. A world above that recedes further and further. During this descent, light first fades. Around 200 meters, sunlight begins to thin. At 500 meters, it is almost gone. At 1,000 meters, it has completely disappeared. From there to the bottom, another 10,000 meters of darkness. The submersible moves through a world that has never seen the sun. The passengers of this vehicle, if any, must contend with this, with the slowness and the darkness and the immensity of what surrounds them. There is no urgency. There is nothing to do but descend and reflect and observe the instruments and let the ocean carry you at its own pace. It resembles, in many ways, falling asleep, a progressive surrender, a slow departure from the familiar world to something calmer, deeper, and entirely its own. Many deep-sea creatures in and around the trench produce their own light through a process called bioluminescence. In the darkness, beyond 1,000 meters, there is no light from above, but there is light nonetheless. It comes from within, from the creatures themselves. Bioluminescence is the production of light by living organisms, and it is extraordinarily common in the deep sea. It is, in fact, one of the most widespread forms of communication and camouflage in the ocean. The majority of deep-sea organisms are believed to produce light in some form or another. The depths are not simply dark. They are illuminated from within by thousands of tiny cold fires, each produced by a creature going about its business in the permanent night. The mechanisms vary. Some organisms harbor light-producing bacteria in specialized organs. Others have chemical reactions that directly produce light in their own tissues. Colors also vary. Although most deep-sea bioluminescence is blue or blue-green, as these wavelengths travel furthest in seawater. Some creatures produce brief flashes, Others glow constantly. Still others draw complex luminous patterns along their bodies that change and transform as they move. The purposes of bioluminescence are as varied as the creatures that produce it. Some use it to attract prey, dangling a luminous lure in the darkness to draw smaller animals. Others use it to startle predators with a sudden flash of light. Some use it to communicate with potential mates. Still others use it as camouflage, mimicking the faint glow of the water above them, so as not to cast a shadow for predators below. Near the Mariana Trench, bioluminescence is more discreet. Many extreme deep-sea creatures glow very faintly, if at all. But in the waters above the trench, the darkness gently pulses with a cold light, a living aurora at the bottom of the sea. The Mariana snailfish is one of the deepest fish ever recorded, found at depths no other fish has reached. Among the most remarkable inhabitants of the Hadal Zone is a small, pale, almost translucent fish called the Mariana snailfish. It belongs to the Liparidae family. It looks, at first glance, like something ordinary. A slender, soft-bodied fish, milk-pale, scaleless, with large eyes that seem slightly too big for its head. But the Mariana snailfish holds a record. It has been filmed and collected at depths greater than 8,000 meters, making it one of the deepest fish ever documented. No other fish has been found deeper. At these pressures, the biochemistry that allows fish to maintain their internal structure becomes extraordinarily difficult, and scientists once believed there was a depth beyond which fish simply could not survive. The Mariana snailfish has pushed that limit, existing at depths once thought impossible for vertebrate life. What makes the snailfish so successful at such extreme depth? In part, its chemistry. Deep-sea fish, under high pressures, accumulate a compound called trimethylamine N-oxide, or TMAO, in their tissues. This compound counteracts the effect of pressure on their proteins, keeping molecules functioning correctly, even as the outside world tries to crush them into a different shape. The deeper the fish lives, the more TMAO it contains. The Mariana snailfish is, at a molecular level, precisely calibrated for the world it inhabits. It lives in groups, moving through the water above the trench floor in small schools, feeding on the tiny crustaceans that swarm in the depths. It is not a spectacular creature. It does not glow, show off, or perform. It simply lives deeply and quietly in the most extreme part of the ocean, perfectly at home. The Challenger Deep has been visited many times by robotic vehicles, each revealing something new. Human beings have only visited the Challenger Deep a handful of times. The engineering challenges, the cost, the risk, all make manned expeditions extraordinarily difficult. But robotic vehicles, unmanned submersibles guided by cables, or programmed with autonomous navigation, have made the journey far more often. Each of these missions has returned with something unexpected. Early robotic surveys found sediment samples teeming with microorganisms. Later missions photographed animals no one had ever seen before. Sonar surveys began to reveal the detailed topography of the trench floor, showing ridges and valleys and geological features invisible to instruments from above. One of the most remarkable robotic surveys used a new generation of autonomous vehicles equipped with high-resolution cameras and sophisticated sampling equipment. These vehicles descended slowly, mapping as they went, and returned with images of creatures moving calmly in the darkness. Snailfish, amphipods, small holothurians, soft-bodied relatives of sea cucumbers drifting slowly over the pale sediment, all living their unobserved lives, completely indifferent to the machines that had come down to observe them. Each time we send a vehicle into the depths, the ocean reveals a small part of its mystery, and each time it reveals how much mystery remains. The trench is generous with its secrets. It offers them one by one, slowly, in its own order, on its own schedule. The pressure at the bottom of the trench is so intense that it compresses seawater itself, making the deep ocean denser than surface water. Water is often considered incompressible. In everyday life, this is essentially true. You cannot squeeze a glass of water into a smaller volume with the force of your hands. But at the pressures encountered in the Mariana Trench, even water is compressed. Molecules are pushed slightly closer together, and the water at the bottom of the ocean is measurably denser than the water at the surface. This may seem like a minor technical detail, but it has real implications for how the deep ocean functions. The density of deep water affects how currents move, how heat is distributed, and how the ocean circulates over time. The great deep currents that sweep through the world's oceans, the slow rivers of cold, dense water that flow along the ocean floor, are partly driven by this density difference. The bottom of the Mariana Trench is part of a global system. The compressed, cold, dense water, there is a node in Earth's largest circulatory system. The movement of water that connects all the world's oceans and plays a profound role in regulating climate. The depths are not isolated. They are part of everything. They breathe with the entire ocean, and the entire ocean breathes with the entire planet. The depths and the surface are always in conversation, even if that conversation takes place over timescales of centuries. Scientists have discovered plastic waste and other pollutants at the bottom of the Mariana Trench. Among the most sobering discoveries made in the Mariana Trench in recent years is the presence of plastic. In samples collected from the deepest parts of the trench and from the bodies of animals living there, scientists have found microplastics, tiny fragments of synthetic materials that have traveled from the surface world to the ocean floor. It is a striking reminder of our connection, even to the most remote places on Earth. Plastic that enters the ocean through rivers and coasts does not simply float on the surface. Some breaks down into tiny fragments small enough to be ingested by marine organisms, and these fragments are carried by currents and by the feeding behavior of animals, gradually descending through the water column. In time, they reach the bottom. In 2018, researchers announced they had found pollutants in amphipods collected from the Mariana Trench at levels comparable to to what might be found in Earth's most polluted coastal environments. The chemicals they found included polychlorinated biphenyls and other persistent organic pollutants, substances that are no longer manufactured, but which persist in the environment for decades, even centuries. The deep ocean was once thought to be beyond the reach of human activity, a place so remote, so deep, so difficult to access that our influence could never penetrate it. This idea can no longer be held. Even the Mariana Trench bears the imprint of the surface world. But knowing this is not a cause for despair. It is a cause for vigilance. The trench has shown patience with us. It will, we hope, continue to do so. The trench is located in a region of the Pacific known as the Western Pacific Warm Pool, the largest basin of warm ocean water on Earth at the surface. There is a magnificent contrast in the geography of the Mariana Trench. The surface waters of the region where the trench is located are among the warmest of all the world's oceans. The Western Pacific Warm Pool, as it is called, lies directly above one of the coldest and most compressed bodies of water on the planet. Heat on the surface, and below, at a distance of almost 11 kilometers, a frigid darkness. The warm surface waters fuel some of Earth's most intense tropical weather systems. The Western Pacific is the birthplace of typhoons, the same storms we call hurricanes when they form in the Atlantic. The heat and moisture of these surface waters feed enormous rotating storms that can span hundreds of kilometers and carry winds of extraordinary speed. None of this, neither the heat, nor the storms, nor the agitation of the tropical surface, reaches the bottom of the trench. The two worlds are separated by 10,000 meters of water and countless ocean layers, each slightly colder and darker than the one before it. The bottom of the trench is as unaware of tropical typhoons as we are of the slow grinding of tectonic plates. The surface world unleashes its fury and shines. The deep world is still. Both exist simultaneously, separated by distance, but sharing the same planet. One reaching for the sun, the other resting in permanent night. The Mariana Trench is home to xenophyophores, some of the largest single cells on Earth. Among the most unusual inhabitants of the Mariana Trench are organisms called xenophyophores. These are single-celled organisms, but they are unlike any single cell you might imagine. They are visible to the naked eye. In fact, some of them are enormous for cells, reaching 20 centimeters or more in diameter. They are, in this respect, the largest single cells known to exist anywhere on Earth. Xenophyophores live on the seabed, forming irregular branching structures that resemble small sponges or pale clumps of material. They collect particles from the surrounding water and sediment, incorporating everything from mineral fragments to tiny shells of dead organisms into their own bodies. Over time, they build complex and fragile architectures of accumulated materials. Despite their large size, they are delicate. The first time researchers tried to collect xenophyophores from the deep, the organisms disintegrated during ascent, unable to survive the change in pressure and handling. Later expeditions used more careful techniques to preserve them, and scientists have been able to study them in more detail. They do not move. They do not pursue prey. They simply sit on the sediment and collect what comes to them, slowly growing over a lifespan that can span years. They are, in their own way, perfect inhabitants of the deep, patient, still present. A submersible viewport must withstand the same pressure as 11,000 meters of water pressing on a small pane of glass. The engineering required to descend to the Challenger Deep is among the most demanding in the world. The pressure at the bottom of the trench would shatter conventional materials, crush ordinary structures, and flood any vessel not specifically designed to withstand it. Building a vehicle capable of reaching these depths and returning is an exercise in precision and meticulousness. The observation portholes, the windows through which passengers observe the depths, must be among the most carefully engineered pieces of glass or acrylic on Earth. They must withstand the full pressure of the water column above them, which, at the bottom of the Challenger Deep, means a force of approximately 1,100 atmospheres pressing on every surface. A porthole, a few centimeters wide, is subjected to forces equivalent to the weight of dozens of fully loaded trucks. The solution involves conical shapes in which the material is pressed more firmly into its seal by the pressure itself, rather than being forced out of it. The greater the pressure, the tighter the fit. It is an elegant piece of engineering, using the very force that threatens the vessel to enhance its integrity. Even so, every descent is a test. The depths do not forgive small mistakes. Every weld, every joint, every piece of hardware on a deep-sea submersible is inspected with extraordinary care before each dive. And even then, the vehicle is only trustworthy because it has survived before. James Cameron made a solo descent into the Challenger Deep in 2012, the first manned solo dive to that depth. Among the handful of humans who have descended into the Challenger Deep is filmmaker James Cameron, who, in March 2012, became the first person to make a manned solo dive to the deepest point on Earth. Cameron had spent years working with engineers to design a specially built submersible called the Deep-Sea Challenger. It was a remarkable vehicle, narrow and vertical rather than the traditional spherical shape, designed to descend quickly and use its time on the bottom efficiently. The descent took approximately 2 hours and 36 minutes. At the bottom, Cameron spent nearly 3 hours exploring the trench floor with cameras and scientific instruments, collecting samples of sediment and organisms. He described the bottom as a barren lunar landscape, though not devoid of life. Amphipods were visible, and the sediment stretched in all directions, pale and still, in a darkness his lights could not entirely penetrate. What Cameron brought back, beyond samples and images, was a sense of the place, its calm, the immensity of the darkness. The way the trench rested at the bottom of its own world, complete and undisturbed, barely touched by the descent of a small vehicle and a curious human. After spending time on the bottom, he released the weights holding his vehicle and slowly ascended to the surface, to the light, to the world of noise, weather, and ordinary things. The journey upward after the depths must feel like waking from a very peculiar dream. The Mariana Trench could hold clues to the origins of life on Earth. Life began on this planet between 3.5 and 4 billion years ago. Under conditions scientists are still striving to understand. One of the leading theories about where and how life first appeared points to the deep ocean, specifically to environments very similar to hydrothermal vents. The chemistry of deep-sea hydrothermal vents is extraordinary. Hot, mineral-rich water mixing with cold seawater creates strong temperature gradients and a constant flow of chemical energy. The minerals themselves, such as iron, sulfur, and hydrogen, can participate in complex chemical reactions that, under the right conditions, begin to resemble the chemistry of living things. Membranes form spontaneously. Molecules polymerize. Complex organic chemicals assemble from simpler components. Some researchers argue that life did not just originate near hydrothermal vents. It originated in the pores and crevices of the rocks around these vents, in tiny chambers where concentrations could build up and reactions occur over geological timescales. The ancestors of all life on Earth, according to this view, were not swimming freely in a primordial ocean. They were huddled in the warm, mineral-rich darkness of the deep seabed, under conditions not entirely different from those found near the Mariana Trench today. If this is true, then the trench is not just the deepest place on Earth. It is, in a sense, the oldest place, the place where it all began. And we are all, in the most literal sense, children of the deep. There are zones within the trench called Hadal Zones, the deepest ecological regions of the ocean, beginning at 6,000 meters. The ocean is divided into zones based on depth, each with its own character, its own community of life, its own particular quality of darkness, pressure, and cold. The shallowest is the sunlit zone, where photosynthesis is possible and life is richest. Below comes the twilight zone, where light fades. Then the midnight zone, completely dark. Then the abyssal zone, the vast flat plains of the deep ocean floor. And beneath the abyssal zone, starting at about 6,000 meters, is the Hadal Zone, named after the Greek underworld. The Hadal Zone encompasses all the deepest ocean trenches, including the Mariana. It is the least studied region of the ocean, the least understood, and the least visited. Only a small fraction of the Hadal Zone has been explored in detail. Within the Hadal Zone, conditions are severe enough that many organisms cannot survive, but those that have adapted to live there are remarkable in their specialization. Hadal species often differ significantly from their relatives in shallower depths, shaped by millions of years of evolution under conditions unique on Earth. They are, in a sense, creatures from another world, a world that exists on our own planet, but operates by its own rules. The Hadal Zone is the frontier of ocean science. Every new expedition there expands the map, adds new species to the list, raises new questions about how life functions in extremes. It is a place where our knowledge is thin and the ocean's secrets are deepest. The currents in the deep ocean move extremely slowly, circulating water on timescales of hundreds, even thousands of years. At the surface, the ocean moves. Currents, driven by wind and temperature, carry water around the globe on timescales of years or decades. Gyres spin in the major ocean basins, carrying warm and cold water in enormous loops. The Gulf Stream carries heat from the tropics to northern Europe. The surface ocean is dynamic, changing, reactive. The deep ocean is different. Below the thermocline, the boundary between warm surface water and cold deep water, the ocean moves on an entirely different timescale. The thermohaline circulation, sometimes called the ocean conveyor belt, drives the slow movement of deep water around the planet. Cold, dense water sinks at high latitudes and flows slowly along the ocean floor towards the tropics. The journey from the North Atlantic to the deep Pacific and back again can take 1,000 years or more. The water currently at the bottom of the Mariana Trench last saw the surface centuries ago, perhaps longer. It has remained in the depths under pressure in darkness, moving imperceptibly slowly throughout its journey around the ocean. By the time it finally rises to the surface, centuries will have passed. This is the timescale of the deep ocean, not days or seasons or human generations, but centuries. The depths operate with a patience that makes almost everything else seem rushed. Some deep-sea organisms can survive without oxygen, living in what are known as anoxic environments. Life, as we generally understand it, requires oxygen. The process of respiration that powers our cells and those of most living things depends on the availability of oxygen. When oxygen runs out, life for most organisms is no longer possible. But in some parts of the deep ocean, oxygen is scarce or absent. Low oxygen areas, called oxygen minimum zones, develop when organic matter decomposes faster than currents can replenish the oxygen supply. And in some extreme deep-sea environments, oxygen is essentially absent. Yet life is present there. Microorganisms called anaerobic bacteria have found ways to derive energy from chemical reactions that do not require oxygen. Some use sulfate, others nitrate, still others process methane. They have effectively rewritten the rules of metabolism, finding pathways through the chemistry of the deep that work perfectly well without the molecule on which almost all surface life depends. These organisms are not mere curiosities. They play a crucial role in the chemistry of the deep ocean, cycling nutrients and chemicals through the sediments in a way that affects the entire ocean system. And their existence expands our understanding once again of where life can exist, not only on Earth, but potentially on other worlds. If life on Earth can survive without oxygen in darkness, under crushing pressure, then the universe of possible habitats becomes very vast indeed. The Mariana Trench is located in an area of the Pacific known for extreme geological activity, sometimes called the Ring of Fire. Around the edges of the Pacific Ocean, a chain of volcanoes seismic zones, and tectonic boundaries, forms an approximate circle that geologists call the Ring of Fire. It stretches from the west coast of the Americas, across Alaska, then Japan and the Philippines, New Zealand, and back across the Pacific. Along this ring, the majority of the world's most powerful earthquakes and volcanic eruptions occur. The Mariana Trench is located within the Ring of Fire. The same tectonic processes that created the trench are also responsible for the volcanic archipelago of the Mariana Islands above it, and the earthquakes that occasionally shake the region. The depths and the surface are connected here by forces that operate far beneath both. The Ring of Fire has shaped the Pacific in fundamental ways. The islands that dot the western Pacific, many of them formed by volcanic activity, are the surface expression of the same geological machinery that created the trench. The volcanoes and the abyss are siblings born of the same tectonic process, one rising to the sky while the other descends into the earth. It is a place of extraordinary geological energy, and yet, from the bottom of the trench, none of this drama is visible. The volcanic islands are 10 kilometers above. The tectonic machinery is unfolding in the rock far below. At the bottom of the trench, all is calm. The earth moves around it, but the depths remain in their own silence. At the center of everything, scientists use acoustic sonar to map the ocean floor, painting pictures of the trench with sound. We cannot see the bottom of the Mariana Trench from the surface. The water is too deep, too dark, too opaque for any light-based observation from the surface. But sound is another matter. Sound travels extremely well through water, and by sending sound pulses downwards and measuring the time it takes for the echoes to return, scientists can build detailed three-dimensional maps of the seafloor. This technique, called multi-beam sonar, involves ships towing arrays of sound emitters and receivers that cover wide swaths of the ocean floor in a single pass. The returning echoes are processed by computers to produce detailed maps showing the depth, topography, and character of the seafloor surface. Over decades of survey work, these maps have revealed the extraordinary complexity of the trench. The Challenger Deep is not a simple, flat basin. It has ridges and valleys, different sections at slightly different depths, geological features sculpted by the continuous collision of tectonic plates. The maps show terraced slopes, sediment flows, and geological structures that take millions of years to form. The depths seen by sonar are as complex and detailed as any landscape on the surface. And yet, despite all that the maps reveal, they are still just maps. They show the shape of the place, but not its texture, not the living creatures moving on the sediment, not the quality of the darkness or pressure or cold. The map is not the territory. The trench is always larger, more detailed, and more itself than any representation we can make of it. The first organisms discovered in the extreme depths of the ocean helped redefine what scientists believed was possible for life. When the very first deep-sea expeditions lowered dredges and nets into the deep ocean in the 19th century, most scientists expected to find nothing. The prevailing theory, championed by the influential naturalist Edward Forbes, held that the deep ocean, beyond about 500 meters, was entirely devoid of life. An azoic zone, no light, no warmth, too much pressure. Nothing could live there. Forbes was wrong. As the Challenger expedition and others brought back material from increasingly greater depths, they discovered organisms, worms, crustaceans, echinoderms, simple but undeniably living creatures, recovered from depths believed to be totally sterile. Each new discovery pushed the limit lower. The boundary of no life kept receding as expeditions went deeper, and eventually, when technology allowed humans and robots to visit the deepest places, the final revelation came. Life was not just present in the deep. It was abundant, specialized, and thriving on its own terms. The story of the discovery of deep-sea life is a story of the danger of assuming we know where the limits of the possible lie. Again and again, the ocean pushed those limits back. Again and again, life was found where it wasn't supposed to be. And each time, the world became a little bigger, a little fuller of possibilities, a little more surprising than before. Surface water takes centuries to reach the bottom of the Mariana Trench through the slow circulation of deep waters. The water at the bottom of the trench has traveled a very long way. It didn't start at the bottom. It started at the surface, somewhere in the cold waters of high latitudes, perhaps the North Atlantic or the waters around Antarctica. There, chilled by polar air and made denser by its salinity, it sank. It began to descend through the water column, driven by its own density, slowly making its way towards the ocean floor. From there, it followed the subtle gradients of the deep ocean, moving imperceptibly, slowly towards the Pacific. The journey took centuries, perhaps longer. The water flowed along the ocean bottom, guided by underwater topography, sinking into the deepest parts of the ocean basin, until it finally found its way into the network of deep trenches that scar the Pacific floor, and eventually, some settled at the bottom of the Mariana Trench. The water you might imagine at the bottom of the Challenger, deep, last, touched the ocean's surface hundreds of years ago. It has been traveling ever since, moving in darkness on a journey measured not in kilometers per hour, but in years per meter. When it finally rises to the surface, upwelling in a remote part of the ocean, it will carry with it the chemistry of the deep, the minerals and nutrients it collected on its long journey, and it will warm in the sun. Gases will dissolve into it, and eventually it will be ready to sink again for another century-long journey. Expedition ships above the trench can feel very lonely, even in the middle of a busy ocean. There is a peculiar loneliness that comes from being on a research vessel above the Mariana Trench. The Pacific is an immense ocean. The region near the trench is remote from major shipping lanes and far from coastlines. In all directions, the horizon offers only water. Scientists who have worked on such expeditions describe a distinct quality of this experience: the awareness that beneath you, at an unfathomable depth, lies the deepest place on Earth, that the ocean floor beneath the ship is not at all close, but separated by a distance greater than most people travel in their daily lives. The ocean here is not shallow. It is the opposite of shallow. It is the deepest depth our planet possesses. And yet, standing on the deck of a research vessel, the ocean looks the same as usual. Waves, wind, the wide horizon, the sun rising and setting on schedule. None of the depths below are visible or felt. The immensity of the trench is entirely invisible from the surface. Perhaps this is one of the most humbling things about the deep. Not only that it is there, but that it is invisible, that one can float directly above one of the most extraordinary places on Earth and see nothing, feel nothing, know nothing, unless one already knows where to look. The world contains depths that are completely hidden from us, even when we stand directly above them. Some species in the trench have evolved transparent bodies, which can offer protection in a world with no light to reflect. In the permanent darkness of the deep sea, being visible is often dangerous. A brightly colored or opaque body is easy for a predator to spot, especially if bioluminescence is nearby. Many deep-sea organisms have evolved strategies to reduce their visibility. Some are jet black, absorbing any light that hits them. Some are red, a color that appears black at depth because red wavelengths of light do not penetrate deeply. And some are transparent. Transparency in the deep sea is a remarkable adaptation. An organism whose body is completely clear essentially disappears. Its tissues let light pass through rather than reflecting it, making the creature effectively invisible to any eyes that might be looking for it. The only parts that tend to remain visible are the digestive organs, which cannot easily be made transparent because they contain food and other opaque materials. Near the Mariana Trench, transparent organisms drift through the water with astonishing variety. Small crustaceans with completely clear shells reveal their internal organs and beating hearts within. Jellyfish float with transparent bells, their trailing tentacles almost invisible until touched. Fish with clear bodies glide through the darkness, barely more visible than the water itself. They do not hide. They are simply not there in a visual sense. They have made themselves out of nothing, in a place where nothing is the dominant color. The Mariana Trench creates its own unique water chemistry, distinct from the open ocean above. Water chemistry is not uniform across the ocean. Different depths, temperatures, pressures, and biological communities all influence the chemical composition of the water. And in the Mariana Trench, where conditions are unlike anywhere else on Earth, the water chemistry has its own particular character. Dissolved oxygen levels at the bottom of the trench are low, but not absent. The slow resupply of oxygen by deep water circulation is just enough to support the aerobic organisms that live there. Although these organisms have generally evolved to function efficiently with the available oxygen, dissolved carbon dioxide levels are higher at depth, which affects the acidity of the water. The deep is generally more acidic than the surface, partly because carbon dioxide is more soluble at lower temperatures and higher pressures. This increased acidity has important implications for organisms that build shells or skeletons from calcium carbonate. Many creatures that thrive in shallower waters would have their shells dissolve in the deep. Below a certain depth, called the carbonate compensation depth, calcium carbonate does not persist. It simply dissolves. This is one reason why the sediment at the bottom of the trench is not dominated by calcium carbonate shells of tiny organisms, as it is in many shallower places, but rather by silica and clay. The chemistry of the deep is its own language, written in the dissolved gases and minerals, and the silent processes of the organisms that live at the extreme. The deepest parts of the ocean were once thought to be static and unchanging, but we now know they are dynamic. For a long time, the deep ocean was imagined as a timeless realm, a place where not much happened and nothing really changed. The stillness and slow currents suggested a world frozen in its own permanence, too remote and too extreme for the dynamism of the surface world to penetrate it. We now know that was wrong. The deep ocean is dynamic, not on the timescale of days or seasons, but on the timescale of decades, centuries, and geological epochs. Deep ocean currents are shifting with climate change, altering the flow of water and the distribution of nutrients and oxygen. The chemistry of the deep is changing as the surface ocean absorbs more carbon dioxide from the atmosphere. Tectonic activity reshapes the trench floor over geological timescales. Even on shorter timescales, the depths are not still. Organic matter falls from above in what scientists call marine snow, a constant, gentle fall of particles from the sunlit world to the dark bottom. Large organisms die in the water above and sink to the bottom, serving as food for the scavenging community of the deep. Occasionally, entire whale carcasses arrive on the ocean floor, providing a sudden bonanza that supports a specialized community of organisms for years. These events, called whale falls, create their own temporary ecosystems. The whale's body goes through stages of decomposition, each stage supporting different communities. Scavengers strip away soft tissues. Then organisms break down the bones, and finally sulfur-reducing bacteria colonize the remaining material, creating a chemistry not unlike that of a hydrothermal vent. A whale fall can support life on the deep ocean floor for decades. The depths listen to the surface. They change with it slowly, on their own terms. Sunlight never reaches the bottom of the trench, making it one of the last truly dark places on Earth. We live in a world saturated with light. Even at night, our streets, buildings, and screens cast brightness into every corner. The night sky carries the light of stars and the moon. The darkest places we encounter are usually temporary. A power outage, a windowless room, an instant of closing our eyes. But the bottom of the Mariana Trench has never seen light. Not once in hundreds of millions of years since the trench formed. The sun rises and sets each day over the Pacific, painting the water's surface gold, then fading back into darkness. The ocean's surface sparkles and shimmers with every photon it receives. And 10,000 meters below, not a single one of those photons arrives. Not a flicker, not a trace. The darkness of the trench is not the darkness of a room with the lights off. It is the darkness of a place that has never known light, that makes no reference to it, that holds no memory of it. It is a quality of darkness unlike anything we experience. A darkness that is not temporary or circumstantial, but simply the permanent and total condition of a place. And yet, life is present there. Creatures that have never seen light, that have evolved entirely in its absence, that need it no more than a forest needs the ocean. They are made for the darkness. They belong to it. Darkness for them is not an absence. It is simply what the world is. There are underwater mountain ranges within the Mariana Trench that have never been seen by human eyes. The Mariana Trench is not simply a flat-bottomed crack in the ocean floor. Its internal topography is complex and varied, shaped by the same tectonic forces that created the trench itself. Sonar mapping has revealed ridges crossing the trench floor, raised walls along its flanks, and sediment flows that have reshaped its surface over time. Some of these internal features are of a significant scale. Ridges within the trench rise hundreds of meters above the surrounding bottom. Walls along the trench's flanks descend steeply, creating a landscape of dramatic vertical relief. Some sections of the trench floor are divided into distinct basins by internal ridges, each slightly different in depth and character. These features have never been seen directly by human eyes. Sonar gives us their shape, their dimensions, their approximate topography, but the detail, the texture of the rock, the life that might cling to the walls, the color and character of the sediment in different sections, all of this is known only to the darkness and what lives within it. The exploration of these internal features is still in its early stages. Every new sonar survey reveals more complexity than the last. The more we map the trench, the more there is to map. The depths reward careful attention with more and more detail, until the map begins to approach the territory itself. And even then, it remains insufficient. The trench's sediments contain chemical signals of events that occurred millions of years ago. The pale sediment that covers the floor of the Challenger Deep is an archive. Not a written record, not something that can be read at a glance, but a chemical and physical archive that encodes the history of the ocean above it in the materials that have flowed to the bottom for millions of years. Scientists studying deep-sea sediments can extract this archive with care. They drill through the layers, taking cores that represent time, with the deepest layers being the oldest. By analyzing the chemical composition of the sediment at different depths, they can reconstruct the conditions of the past ocean: temperature, chemistry, types of organisms that lived in the surface waters above, the presence or absence of oxygen, even the chemical fingerprints of major geological events like volcanic eruptions or asteroid impacts. The Mariana Trench sediment contains tens of millions of years of this history. Somewhere in these layers is the chemical record of the mass extinction that ended the dinosaurs 66 million years ago, when an asteroid hit Earth and changed everything. Somewhere in these layers is the record of the Paleocene thermal maximum, when Earth's temperature rose sharply and the oceans became more acidic. All of this is there, recorded in the silent accumulation of particles over geological time. The bottom of the trench is not just a place. It is a memory. At the deepest points of the ocean, creatures live in a world entirely shaped by chemistry, not by sunlight. The energy that powers almost all life on Earth comes from the sun. Plants capture sunlight and convert it into chemical energy. Animals eat plants. Other animals eat those animals. The sun is the source, and everything that follows depends on photosynthesis, directly or indirectly. In the deep ocean, and particularly in the Hadal Zone, sunlight is irrelevant. There isn't any. The organisms there cannot depend on photosynthesis, because photosynthesis requires light. Instead, they depend on something else: chemistry. Two main pathways provide energy to deep-sea communities. The first is the slow rain of organic matter from above. Dead organisms, fecal pellets, fragments of algae, and other materials that sink through the water column. This matter carries chemical energy, initially captured by photosynthesis at the surface, but transformed and concentrated during its journey downwards. Deep-sea communities that depend on this matter are ultimately still powered by solar energy, but at multiple removes. The second pathway is chemosynthesis. Near hydrothermal vents and cold seeps, microorganisms can derive energy directly from chemical reactions, particularly the oxidation of hydrogen sulfide and other compounds. These organisms form the base of food webs, entirely independent of the sun. They are the only organisms on Earth that live completely outside the solar energy budget, sustained by the Earth's own heat and chemistry. These communities are among the most independent forms of life known. They belong to the deep in the fullest sense. They have never been part of the surface world. They do not need the sun. They have their own energy, their own darkness, their own way of being alive in the world. The exploration of the deep ocean remains one of the greatest scientific challenges of the 21st century. We have sent spacecraft to the Moon and Mars. We have mapped the surface of Venus through sulfuric acid clouds using radar. We have launched telescopes into orbit capable of seeing galaxies billions of light years away. We have probed the structure of subatomic particles and decoded the genomes of thousands of species. And yet, less than 20% of the ocean floor has been mapped with any resolution. The Hadal Zone, the deepest region of the ocean, has been visited only a handful of times by manned vehicles. Vast stretches of the deep ocean floor have never been directly observed at all. In many ways, the deep ocean is the least understood environment on Earth. The challenges are real. Building vehicles capable of withstanding the pressure of the deep is difficult and expensive. Operating in an environment where communication is almost impossible, where instruments fail, where everything must work perfectly without any possibility of external help, requires extraordinary engineering. Funding for deep-sea research competes with other scientific priorities and is often insufficient. But the scientists who dedicate their careers to the depths do not seem discouraged by this. They describe their work as explorers have always described the frontier, with a sense of privilege, of standing on the edge of what is known and looking out into what is not. Every dive is a first. Every sample brings something new. Every descent into the darkness is a journey into a world that has never been seen before. The snailfish, the deepest fish known to science, has no scales, and its skin is so delicate it tears if handled roughly. Imagine a creature entirely designed for depth, not for strength, speed, or spectacular display, but simply to exist at a pressure that would crush almost any other vertebrate on Earth. The Mariana snailfish has shed many features common to fish that live in the light. Its scales are gone, replaced by soft, slightly gelatinous skin. Its bones are flexible, not the rigid structures of surface fish, but something more yielding, less likely to collapse under pressure. Its color is a pale white, almost translucent, or slightly pinkish, depending on the individual, and the light used to observe it. Its eyes are relatively large, although in the absolute darkness of the deep, even large eyes can detect only the faint bioluminescent glows of other creatures. It is a soft-looking animal, delicate in a way that seems contradictory for something living in such extremes. Researchers who have managed to collect snailfish from the deep report that it is almost impossible to keep them in recognizable form. The pressure change from the deep to the surface is devastating for tissues adapted to depth. The fish essentially disintegrate during ascent, their bodies unable to maintain their structure in the very different conditions of shallow water. They are creatures of a specific world and cannot leave it. They are as precisely adapted to their environment as the environment is to them. Perfectly placed, perfectly adapted, belonging to the depths as completely as any creature belongs to any place on Earth. The Mariana Trench has inspired poetry, fiction, and scientific curiosity for as long as it has been known. Ever since the Challenger expedition first measured the extraordinary depth of the trench, it has held a grip on the human imagination that goes far beyond the purely scientific. There is something about the existence of such a place right here on our own planet, hidden beneath the ordinary-looking surface of the Pacific, that resonates with something deep within us. The idea of the trench has appeared in novels, films, poems, in the quiet contemplations of people who have simply heard of it and found themselves unable to stop thinking about it. It represents, in the imagination of many, the ultimate unknown, the limit of the knowable, the place where the ordinary world ends and something else begins. But it is not truly unknowable. It is simply hard to reach. And with each expedition, each robotic survey, each carefully collected sample, the mystery shrinks a little and knowledge grows. The trench was unknown to humans until the 1800s. It was completely unmapped until the 20th century. It was first visited in person only in 1960. And now we know its shape, its resonance, its chemistry, its geology in detail that would have astonished the sailors who first lowered a weighted line into its darkness. The mystery does not disappear with knowledge. It transforms. The more we know about the trench, the more remarkable it becomes. Not less, but more. Knowledge of the depths only deepens the wonder. The ocean as a whole covers over 70% of Earth's surface, and most of it remains unexplored. The Mariana Trench is the most extreme point of a vast and largely unknown world. The ocean covers approximately 71% of Earth's surface, an area so vast that all the continents could fit within it with room to spare. And the average depth of the ocean is about 3,800 meters. It is not a shallow place. The ocean is, in volume, the dominant habitat on Earth, yet it remains the least explored. Scientists estimate that over 80% of the ocean floor has never been directly observed. This means that most of our planet's surface, including its mountains, valleys, volcanoes, and plains, has never been seen. We have a better map of the moon's surface or Mars's surface than of the bottom of our own ocean. This is changing. New technologies, including long-range autonomous underwater vehicles and improved sonar systems, are accelerating the mapping of the ocean floor. Each year, a little more of the unknown becomes known. Each new survey reveals terrain, life, and geological features that had never been documented before. But the pace of exploration is slow compared to the ocean's size, and the ocean is very patient. It does not rush explorers. It waits as it has always waited in its darkness, cold, and immensity, guarding its secrets with perfect equanimity. Foraminifera, tiny shelled organisms, rain down on the trench floor in vast quantities every day. Among the most numerous contributors to deep-sea sediments are organisms so small they are invisible to the naked eye. Foraminifera are single-celled organisms, relatives of amoebas, that build complex shells around themselves from calcium carbonate or other materials. They drift in the sunlit surface waters in astounding numbers, billions of them in every cubic meter of water in productive regions. They feed, reproduce, live their brief lives, and then die. When they die, their shells sink. They drift slowly downward through the water column, a constant, gentle snowfall of tiny structures, each no bigger than a grain of sand, each a small work of biological architecture. Some are spiral-shaped, some are multi-chambered. Their internal structure is arranged in patterns of remarkable geometric elegance. Each shell is a record of the organism that built it and the conditions of the water it lived in. After sinking through potentially thousands of meters of ocean, they arrive at the deep seafloor. In shallower regions, their shells accumulate and form thick layers of sediment. But in the deepest parts of the ocean, the increased acidity and pressure dissolve calcium carbonate before it can settle, and the shells never arrive. The sediment at the bottom of the Mariana Trench is shaped in part by this dissolution chemistry, which filters out the calcium carbonate remains and leaves behind only the most resistant materials. But in the waters above the trench, foraminifera continually fall. It is one of the quietest and most persistent processes in the ocean. No sound, no light, just the slow, constant rain of tiny shells drifting from the living world above to the dark world below. A connection between two realms, as gentle and continuous as breathing. Cold seeps, like hydrothermal vents, create oases of life in the deep by releasing chemicals from the ocean floor. Not all of the chemistry that supports deep-sea life comes from hot water escaping from below. In some places along continental margins and in deep trenches, cold water slowly seeps up through cracks and fissures in the rock, carrying with it dissolved methane and hydrogen sulfide from organic-rich sediments. These are cold seeps, and like hydrothermal vents, they host rich communities of life entirely independent of the sun. Cold seeps were first discovered in the 1980s in the Gulf of Mexico, and they have since been found in many locations in the world's oceans, including near subduction zones like the one that created the Mariana Trench. Near these seeps, bacteria use the chemical energy of methane and hydrogen sulfide to produce organic matter, which then forms the base of a food web unique in the sunlit ocean. Tube worms cluster around cold seeps, some growing several meters long, living for centuries. Clams with unusual biochemistry colonize nearby sediments. Mussels form dense beds. Small crabs and other crustaceans move within the community, feeding on bacteria and other organisms. The cold seep community is slower and calmer than that of a hydrothermal vent. The water is cold. The chemicals arrive more slowly. The energy is more diffuse. The organisms that live there tend to grow slowly and live long. A tube worm at a cold seep can live 200 years or more, growing slowly in the darkness, sustained by the Earth's chemistry. These communities are among the oldest places in the ocean. Not old as a museum is old, but living in their antiquity, still doing what they have done for millions of years, still transforming the Earth's chemistry into life. The Mariana Trench plays a role in the global carbon cycle by trapping organic carbon in its deep sediments. Carbon cycles through Earth systems in an enormous, slow cycle. It enters the atmosphere as carbon dioxide. Plants and oceanic phytoplankton absorb it and convert it into organic matter through photosynthesis. This matter is eaten, decomposes, and some returns to the atmosphere, but a fraction of it escapes this cycle entirely. In the ocean, some of the organic matter produced in the sunlit surface water sinks before it is fully decomposed. It drifts down as marine snow, dead organism bodies, particles of all kinds, and some reaches the deep seafloor before being decomposed. There, it is buried in the sediment, and carbon buried in deep marine sediment can remain there for millions of years, effectively removed from the active carbon cycle. The Mariana Trench, due to its depth and the unusual chemistry of its sediment, plays a role in this carbon burial process. Organic matter that reaches the bottom of the trench is partially processed by microbial communities living in and on the sediment, but some is buried, incorporated into the trench's geological record, removed from the ocean and atmosphere for timescales that dwarf any human consideration. This process, occurring across the entire deep ocean floor, is one of the mechanisms by which Earth regulates its own carbon budget over geological time. The deep ocean is not just a passive receiver of surface world activity. It is an active participant in the chemistry of the entire planet. Scientists studying the trench have found evidence that microbes can survive inside the sediment itself, deep beneath the surface of the ocean floor. The sediment at the bottom of the Mariana Trench is not an inert layer of accumulated material. It is alive, not with the visible creatures that move on its surface, but with microorganisms, bacteria, and archaea that live inside the sediment, sometimes extending several meters beneath the ocean floor's surface, surviving in conditions that make the deep ocean itself hospitable by comparison. These deep sediment microbes live in darkness, with little or no oxygen, under extraordinary pressure, with virtually no nutrients. They are among the most extreme organisms on Earth, and also among the most numerous. The number of microbial cells living in the ocean floor sediments of all the world's oceans is estimated to be comparable to the number of cells of all plants and animals living on the surface combined. The majority of Earth's biomass, by some calculations, is microbial and lives in the rocks and sediments beneath the ocean floor. These microbes are exquisitely slow. Their metabolism operates at speeds almost impossible to measure by ordinary means. Some researchers believe that individual microbial cells in deep sediments may divide only once every few thousand years, or even less frequently. They do not sleep. They are simply alive at a pace so slow that time is a very different thing for them than it is for us. To study them, scientists drill through the sediments and rocks, collecting cores that must be handled with extraordinary care to avoid contamination. And what they find, even meters beneath the ocean floor, is life. Faint, slow, patient, unimaginable life, always present, always processing chemistry, always being alive in the only way they know. The unique biology of deep-sea creatures offers scientists new insights in medicine and biotechnology. Life in the extreme conditions of the deep ocean produces biochemistry that exists nowhere else. Enzymes that function at high pressure, proteins that remain stable at near freezing temperatures, membranes that maintain their fluidity in conditions that would solidify the lipids found in most organisms. The chemistry of deep-sea life is a toolbox built by evolution for a very specific and very demanding world. And it turns out that this toolbox has potential applications far beyond the deep ocean. Scientists have studied deep-sea enzymes with enormous interest because enzymes that function well at extreme temperatures and pressures often also function well in industrial processes involving these same conditions. Cold-active enzymes derived from organisms that live near the freezing point of water can catalyze chemical reactions at low temperatures that would normally require heating, thereby saving energy in industrial applications. Deep-sea bacteria have also become a target of medical research. Novel compounds produced by deep-sea microorganisms, compounds that have evolved for purposes unique to their environment, sometimes have remarkable biological activity in human systems. Some have shown promise as antibiotics, anti-cancer compounds, or anti-inflammatory agents. The pharmaceutical industry is increasingly interested in the biochemistry of the deep ocean as a source of novel molecules. The depths are not just a place of pure scientific curiosity. They are a reservoir of biological innovation accumulated over millions of years of evolution in a unique and demanding environment. Every species that lives there is a library of solutions to problems we have not yet fully understood. The way nutrients cycle in the Mariana Trench differs fundamentally from shallower ocean ecosystems. In the sunlit surface waters, nutrients cycle relatively quickly. Phytoplankton take up nutrients and grow. They are eaten. Their predators are eaten. Eventually, nutrients return to the water through excretion and decomposition. The cycle plays out over weeks or months. In the Mariana Trench, the nutrient cycle is entirely different. The organisms there receive their nutrients from above in the form of organic matter sinking from the sunlit zone. This matter arrives slowly and irregularly. It is not a constant supply, but a gradual, unpredictable rain. Deep-sea organisms have evolved to make the most of what arrives. When something does arrive, the response can be dramatic. A large piece of organic matter landing on the trench floor is quickly colonized by bacteria that begin to break it down. Amphipods and other scavengers quickly arrive, drawn by chemical signals in the water. Within days, a carcass that took years to reach the bottom can be almost entirely consumed. But between these events, the deep-sea community must subsist on very little. Bacteria in the sediment process, organic matter incorporated into the sediment. Over time, larger organisms move slowly, conserving energy, waiting for the next delivery from above. It is a life organized around scarcity and patience, around the ability to do without, and to make the most of what comes when it comes. The Mariana Trench has been designated as part of a U.S. national monument, protecting it from exploitation. In 2009, President George W. Bush created the Mariana Trench Marine National Monument, protecting the waters and seafloor of the Mariana Trench and the surrounding area. The monument encompasses the Mariana Trench itself and the volcanic arc and islands associated with the subduction zone. The creation of the monument reflected a growing recognition that the deep ocean, long thought to be too remote and extreme to need protection, was in fact vulnerable to human activity. Deep-sea mining interests had begun to view hydrothermal vents and mineral-rich seafloor sediments as potential sources of precious metals. Fishing operations had demonstrated their capacity to impact even very deep populations of some species, and the accumulation of pollutants in deep-sea organisms, including those in the Mariana Trench itself, showed that human influence could reach even the most remote corners of the ocean. The monument designation does not mean the trench is closed to scientific research. Research expeditions can still obtain permits to visit and study the area. What it prevents is commercial exploitation of the trench's resources. No mining, no commercial fishing. The trench, within the monument's boundaries, is protected as a natural area. It is a small mark of recognition from the surface world that the deep deserves to be left largely to itself. That the patience of the trench, which has existed for tens of millions of years without human intervention, deserves to be honored. Microbial mats cover vast areas of the trench floor and serve as a foundation for other life forms. In many parts of the trench floor, and in areas surrounding hydrothermal vents and cold seeps, thick mats of bacteria cover the sediment. These microbial mats are sometimes visible in images collected by remote-controlled vehicles, appearing as pale or orange films on the seabed. They can extend for considerable distances, covering the sediment with a living layer. The bacteria in these mats are the primary producers of the deep. They are not photosynthetic, but chemosynthetic, using the chemical energy of the compounds around them to produce organic matter. Other organisms feed on these mats, grazing on them as land animals graze on grass. Small crustaceans burrow through the mat. Worms tunnel through it. The mat provides both food and habitat for a community of small organisms that would not otherwise survive. Microbial mats are ancient. They are the direct descendants of the earliest communities of life on Earth, which grew as mats in shallow seas over 3 billion years ago. In the deep ocean, far from the evolutionary pressure that led so many groups of organisms to develop complex bodies and specialized behaviors, microbial mats have persisted essentially unchanged for eons. They are, in the most literal sense, the oldest form of life on Earth, still doing what they have always done in the darkness at the bottom of the sea. There is something profoundly soothing in that. The same kind of life that was present when our planet was young is still present at the bottom of the Mariana Trench, living in darkness, transforming chemistry into existence, patient beyond any human measure of patience. Scientists use specially designed pressurized chambers to study deep-sea organisms in conditions that mimic their natural habitat. One of the great challenges of deep-sea biology is studying organisms that cannot survive the change from their natural environment to the surface. Most deep-sea creatures, caught in a net or trap and brought to the surface, do not survive. The pressure change is too rapid, too extreme. The organisms effectively decompress, their tissues unable to maintain their structure in the very different conditions of the surface ocean. To address this, engineers and scientists have developed specially designed pressurized chambers that allow deep-sea organisms to be kept alive in conditions that mimic their natural habitat. These chambers maintain high pressure and low temperature and allow researchers to observe the behavior of deep-sea organisms under controlled conditions. The results of this work have been illuminating. Deep-sea amphipods kept at high pressure in the laboratory can be observed feeding, moving, and reproducing. Their behavior at depth proves to be very different from their behavior at reduced pressure. They are more active. They feed more efficiently. They navigate differently. The laboratory conditions that reveal the most about them are those that most closely match the bottom of the trench. Deep-sea bacteria grown at high pressure produce different compounds, grow at different rates, and behave differently in almost every measurable way compared to surface pressure. They are literally different organisms in functional terms at depth than at the surface. Pressure is not just a background condition. It is a fundamental part of who they are. Deep ocean floors of the world's deep trenches remain among the most pristine environments on Earth. Despite the evidence of pollution that has been found even in the Mariana Trench, the deep ocean floors remain among the least disturbed environments on our planet. No roads have been built across them. No forests have been cleared. No agricultural chemicals have been applied to them. No cities lie above them. The vast majority of the deep ocean floor has never been seen, never sampled, never touched. This pristine quality is partly just a result of inaccessibility. The deep ocean is hard to reach and expensive to study. Its remoteness has protected it from most human activity by default, not by intent. But the result is that we still have on our own planet environments as close to a natural state as any wilderness on Earth. The species that live in these environments have not been subjected to hunting, habitat destruction, the introduction of invasive species, all the pressures that have devastated so many surface ecosystems. They live in the context for which they evolved, surrounded by the conditions they have always known. This is increasingly rare. Much of the surface world has been altered by human activity to such a degree that it is hard to see what it once was. But the deep ocean still offers us a glimpse, a view of life functioning on its own terms, in its own time, in its darkness, as it has for millions of years. That glimpse is precious, and we would do well to protect it. Some deep-sea fish have eyes adapted to detect even the faintest traces of bioluminescence. In a world where the only light is produced by the creatures themselves, eyes have evolved to detect extraordinarily small amounts of it. Many deep-sea fish have enormous eyes relative to their body size, large visual surfaces that collect every available photon. But size alone is not the only adaptation. The visual pigments in the eyes of deep-sea fish have adapted to be most sensitive to the wavelengths of bioluminescence common in their environment. Since most bioluminescence in the deep ocean is blue or blue-green, the visual systems of deep-sea fish are tuned to these colors. They are in essence specialized instruments for detecting the specific quality of light produced by the organisms around them. Some deep-sea fish can detect light at levels so faint that they verge on physically impossible for any biological system. They see in conditions that are essentially dark by any surface standard. A single photon arriving at the right receptor can trigger a response. These animals live at the very edge of what is physically possible for vision. And yet, what they see is presumably a world of flickers and intermittent glows. A cold, blue-tinged world punctuated by brief sparks of light, the constant bioluminescence of a nearby organism, the sudden flash of a startled creature, the steady glow of a lure drifting in the darkness. Not much, but enough. Enough to navigate, to hunt, to avoid being hunted, enough to live in the darkness. The deep ocean has inspired some of humanity's most enduring myths of monsters and mystery. Long before science understood what lived in the deep ocean, people knew the sea had unimaginable depths. The ocean was vast, dark, and unknowable. And from that darkness, imagination conjured creatures of extraordinary scale and menace. Sea serpents, krakens, leviathans. The monsters of myth were in many ways expressions of the same feeling that drives scientists into the deep today. The knowledge that something extraordinary is out there, beyond the reach of ordinary sight. The kraken of Norse mythology was imagined as a creature so enormous it could be mistaken for an island dragging ships into the depths with arms as wide as a sailing ship. The sea serpents on medieval maps, labeled with words meaning "here be dragons," were the cartographic expression of a real uncertainty. The ocean's depths were real. What lived there was unknown, and the unknown for a storytelling species is never an empty place. It turns out the deep ocean does contain creatures of remarkable and sometimes disturbing forms. The giant squid, long the subject of sailors' tales, is real. It can reach lengths of over 12 meters. It has the largest eyes of any known animal. Eyes as large as dinner plates, adapted to detect bioluminescence in the depths. It has been seen alive only rarely, and most of what we know of it comes from specimens found in the stomachs of sperm whales. The anglerfish, with its nightmarish bioluminescent lure and extraordinary sexual dimorphism, is real. The viperfish, with its teeth so long it cannot close its mouth, is real. The barrel-eye fish, with its transparent, fluid-filled domes above its eyes, is real. The deep ocean has repeatedly provided creatures that would seem fantastical if not documented by cameras and scientific collections. The monsters were in their own way correct. The deep ocean contains wonders. They are simply different from those we imagined. The Mariana Trench reminds us that our knowledge of our own planet is still very incomplete. It is easy, in the age of satellite imagery and global communication, to think that Earth has been entirely mapped and entirely known. We can look at our planet from space. We can zoom in on any point on the land's surface with fine enough resolution to see individual buildings. We can track the movement of weather systems across entire continents in real time. The surface world is known to us in extraordinary detail. And yet, beneath the ocean's surface, which covers over 70% of the planet, lies a world that is largely unmapped and almost entirely unexplored. We have measured the shape of the ocean floor with sonar, but our maps lack the resolution to show features smaller than a few hundred meters. The detailed topography, geology, biology, chemistry of most of the ocean floor are essentially unknown. The Mariana Trench is a reminder of the scale of our ignorance, not as an accusation, not as a source of shame, but simply as a fact. The world is larger than our knowledge of it. There is more to discover than has been discovered. The frontier is real, and it is here on our own planet, beneath our feet. This is, in the quiet hours of the night, a beautiful thought. Not everything is known. Not everything has been seen. There is still mystery in the world. There are still places that have never been seen by human eyes, that carry their wonders in perfect privacy, that exist entirely on their own terms. The Mariana Trench is the deepest of these places, but it is not the only one. The world is full of depths, and all of them deserve to be approached with patience, wonder, and a willingness to be surprised. The deep ocean has its own seasonal rhythms, driven by events far above on the surface. We tend to think of seasons as a surface phenomenon. The tilt of the earth, the changing angle of the sun, the warming and cooling of the air, the blooming of plants, and the migration of animals. All of this unfolds in the world of light and weather. But the deep ocean maintains its own relationship with the seasons, indirect and delayed, mediated by the long journey from surface to bottom. In spring and summer, in productive ocean regions, the sunlit surface waters bloom with phytoplankton. The abundance of food at the surface drives an abundance of animal life. And all of these organisms, in living and dying and shedding waste, contribute to the marine snow that sinks to the bottom. When the surface blooms, the amount of organic matter reaching the deep bottom increases. When the surface settles in winter, the supply slows. The deep-sea community feels this, not immediately. Particles take weeks or months to sink from surface to bottom. The signal is delayed and diffused by the journey, but it arrives. Deep bottom organisms have been found to show seasonal patterns in their feeding behavior and population dynamics, responding to the annual pulse of organic matter from the world above. It is a remarkable connection. The deep bottom in permanent darkness, in constant cold, is somehow attuned to the rhythm of a sun it has never seen, receiving signals from a world of seasons that is entirely foreign to its own experience. The surface and the depths, so different, so separated, communicate silently through the slow fall of particles. The geology beneath the Mariana Trench is some of the oldest oceanic crust on Earth. The crust that forms the floor of the western Pacific Ocean is among the oldest oceanic crust on Earth. Unlike continental crust, which can persist for billions of years, oceanic crust is continuously recycled. New crust is created at mid-ocean ridges where magma rises from below, and old crust is destroyed at subduction zones where it plunges back into the Earth's interior. The Pacific Plate, which is being subducted at the Mariana Trench, carries crust that formed at mid-ocean ridges as long ago as 180 million years during the Jurassic period. This means that the rock currently sliding beneath the Mariana Plate, dragging the trench floor into the earth, was created when dinosaurs were still alive, and when the continents were arranged in completely different configurations from their present positions. The trench, in a sense, is a machine for destroying ancient geology. The old, dense Pacific crust descends into the Earth's interior, where it is melted and reincorporated into the mantle. The water it carries, trapped in the minerals of the seafloor sediment, is released into the overlying rock, driving volcanic activity. The chain of volcanic islands visible on the surface, the Marianas themselves, are the direct result of this process. Old crust descends. New volcanic rock rises. Destruction and creation. The same process, the same place, operating for 180 million years, patiently without interruption. Deep-sea creatures that drift to shallower depths often die from the pressure change, demonstrating how precisely adapted they are. The adaptation of deep-sea creatures to their environment is not just functional, it is total. There is no wiggle room, no flexibility, no ability to live in another world. A snailfish at 8,000 meters is not just comfortable there. It is made for that depth and no other. Bring it up, even a few hundred meters, and its biochemistry begins to fail. This is why so few deep-sea organisms are ever seen alive at the surface. Occasionally, a creature from intermediate depths will be found floating on the surface, stranded on a beach, or encountered by a ship. It is almost always dead or dying, its tissues failing in the low-pressure environment. Its internal chemistry is unable to function properly so far from home. Xenophyophores disintegrate on ascent. Snailfish dissolve. Amphipods cease to function. Each organism is so precisely calibrated to its own depth that any significant deviation is fatal. They cannot explore. They cannot migrate upwards to see what lies above. They are fixed in their world as firmly as if they were embedded in rock. In one way, this seems like a limitation, but in another, it is the purest form of belonging. These organisms do not need to be anywhere else. They do not seek another environment. They have found, through millions of years of evolution, the exact conditions that suit them perfectly, and they remain there, perfectly at home in the darkness, cold, and immense patient pressure. The silence of the deep ocean is a silence unmatched on Earth's surface. There are quiet places on the Earth's surface, a library late at night, a forest after heavy snow, a desert at 3 in the morning, far from any road, a mountain lake on a windless autumn day. These are places where the noise of human civilization fades, and you can hear something closer to the world's original quiet. But even the quietest places on Earth's surface carry sound. The movement of air, the ticking of cooling rocks, the distant rumble of the planet's machinery. And at night, the sounds one only hears when everything else is still. Insects, the creaking of a tree, the very faint, distant sound of human activity carried on the wind. The bottom of the Mariana Trench is quieter than any of these places. Not because it is silent, for as we said, sound travels easily through water, and the trench receives echoes from very far away. But it is quieter in a different way. There is no wind at the bottom of the trench, because wind is a surface phenomenon. There is no air. There are no insects, no rustling vegetation, no cracking of expanding or contracting materials warmed by a sun that cannot reach it. The sounds of the deep are aquatic sounds, the passage of distant earthquakes through the rock, the slow movement of deep currents, the gentle disturbances made by creatures moving on the sediment. And above all this, at unimaginable distances, the faint echoes of a world that seems, from the bottom, very far away. It is the sound of a place that has found its own peace. Deep in the darkness, at the bottom of everything, in a quiet that has persisted longer than we can imagine. This quiet is there right now. As you rest, as the world around you quiets, as your breath slows and your thoughts soften, this quiet is at the bottom of the Pacific, unchanged and unmoving. Some silences are greater than others. Some go deeper, and the deepest silence on earth rests at the bottom of the Mariana Trench, patient and perfect, where it has always been. The deep ocean will continue to be explored, and each expedition adds to a story that is still being written. There is no end to the story of the Mariana Trench. It is still being written by the scientists who study it, the engineers who build the vehicles that descend into it, the biologists who catalog its creatures, the chemists who analyze its sediments, the geologists who map its shape. And it is written by the trench itself, by the tectonic forces that still reshape its bottom, by the organisms that still adapt to its extremes, by the water that still circulates in its darkness on timescales of centuries. Each time we lower a camera into the depths, we see something that has never been seen before. There is a particular kind of scientific moment that is almost impossible to describe to someone who has not experienced it. It is the moment when an image arrives from a place it has never come from before. When a camera on a remote-controlled vehicle reaches the bottom of an unexplored section of the trench, and the screen in the control room on the ship above begins to show a landscape that no human eye has ever beheld. The researchers watching that screen see sediment and perhaps rocky ridges and perhaps nothing obvious at first. And then something moves. An animal, unknown or poorly known, going about its life with complete indifference to the machine that has just arrived to observe it. The researchers lean forward. Someone reaches for a notebook. Someone begins to record. A quiet conversation begins about what they are looking at, what it might be, if it has ever been documented before. This happens virtually every deep-sea expedition that reaches unexplored territory, not always dramatically. Sometimes the novelty is a species already known from other trenches, now confirmed in a new place. Sometimes it is previously undocumented behavior. Sometimes it is a creature no one in the room can immediately identify, and that will require months of analysis by specialists before it is understood. But it happens. trench continues to give, and each new image, each new sample, each new data point is a brick in the edifice of knowledge that humanity is slowly, patiently building, expedition by expedition, about the most extreme environment on our own planet. Future generations will know things about the Mariana Trench that we cannot imagine. Technology will improve. Visits will become more frequent. Biology, geology, and chemistry will be mapped with increasingly precise detail. And yet, in all likelihood, there will still be more to discover. The trench is large enough, complex enough, and patient enough to sustain our curiosity for as long as we choose to exercise it. In the meantime, what we have is remarkable. A place 11 kilometers below the surface, a world of darkness, pressure, and cold that has existed for tens of millions of years. A community of creatures adapted to conditions unlike anything else on Earth. A geological process of enormous power and patience. An archive of planetary history written in the sediment. All of this resting quietly at the bottom of the Pacific Ocean. Right now, as you rest, the trench is there. It has always been there. And in the quiet of the night, knowing that it exists, knowing that it is there beneath the ocean's skin, patient, full, and entirely itself, is a comfort of a very particular kind. The kind that comes from knowing the world is larger than we think, and fuller of wonders, and fuller of life, and more capable of surprise. We did not choose to live on a planet with a place so deep and extraordinary beneath its oceans. But we do, and it is there for us to think about on nights when thinking about something vast, calm, and unhurried is exactly what is needed. The Mariana Trench, 11 kilometers deep in darkness, in cold, full of life, geology, chemistry, and mystery, is exactly that kind of immensity, exactly that kind of calm. The trench has heard none of our noises. It has felt none of our urgencies. It has not been touched by our seasons or our centuries. And yet, in knowing it, in holding the idea of it in mind on a quiet night, something in us responds to it. Something recognizes the value of that depth and stillness. Something in us is grateful, deeply and quietly grateful, that such a place exists. That not everything on this planet moves at our speed or asks to be seen or needs anything from us. The trench is just there, waiting, patient, complete. And so are you tonight. The next expedition will find something new. It will always find something new. The deep ocean is not the kind of place that runs out of surprises. It is the kind of place that generates them quietly and persistently from a depth of possibilities that has not been exhausted in millions of years. And all of this is happening right now as you rest here at the bottom of the Pacific. In a darkness you will never see, in a cold you will never feel, creatures are moving. Chemistry is working. Earth's plates are shifting by a few millimeters. Sediments are falling particle by particle, adding another infinitesimal layer to the archive of the deep. Trench does not sleep, but it is wonderfully, profoundly silent. And in that silence, there is something that makes our own rest feel very natural, very right. The deepest place on Earth rests in its own kind of stillness, and in the dark hours of the night, we can rest with it. And so, dear listener, We have traveled together to a place both incredibly remote and yet intimately connected to all that we are and all that our planet is. We have descended slowly and gently through the layers of the ocean, through the sunlit surface where waves catch the light, through the twilight zone where daylight fades to blue, through the midnight zone where darkness becomes total, down to the bottom of the Challenger Deep, the deepest, strangest, most patient place on Earth. We have encountered the snailfish, pale and soft, perfectly formed for depths that would destroy all that is familiar to us. We have drifted with the amphipods in countless thousands, moving in the cold and darkness with quiet efficiency. We have rested in the sediment, listening to the slow accumulation of millions of years. We have felt, in a discreet way, the weight of all that water above us, pressing not with violence, but with an ancient and constant calm. The trench has been there for tens of millions of years. It will be there for tens of millions of years more. The plates will continue to move. The sediments will continue to fall. The creatures of the deep will continue to live their lightless lives with extraordinary grace and patience. And the ocean above will continue to carry its storms, its currents, and its light. And none of that will reach the bottom, and the bottom will not care. There is a lesson in that, perhaps a kind of permission. The world above is always moving, always lit, always asking something of us. But the deepest thing we know exists in its own quietness, at its own pace, on its own terms. And everything is fine down there. Everything is exactly as it should be. Let that image carry you now. The pale bottom of the Challenger Deep, soft with sediment, still and cool. The faint flicker of a bioluminescent creature drifting in the darkness. The slow fall of particles from a world too distant to be seen. The patient, unhurried presence of Earth's oldest, deepest, most unwavering place. Let your breath slow to match it. Let the weight of the day settle, as sediment settles gently and unhurriedly, finding its place on the bottom of something vast, silent, and entirely at rest. You are safe here. The depths hold you. The ocean holds you. The entire planet, immense and extraordinary, holds you as it always has. Effortlessly and endlessly. Close your eyes. Breathe slowly and drift, as everything drifts in the depths, gently towards stillness, towards silence, towards the soft darkness where nothing is asked of you and everything is all right. Good night.